Hello and welcome to the MOOC, NPTEL MOOC on Applied Electromagnetics for Engineers. This is the first module where we properly begin the study of electromagnetics, but we will do so in a slightly different manner than what we usually are comfortable with or usually taught with. Usually you start with some mathematics of vectors and vector analysis, calculus, vector fields, then move on to electrostatics, magnetostatics, then introduce Maxwell's equations rather by Faraday's law, and then introduce Maxwell's equations, and then start looking at the applications of Maxwell's equations. We will not take that route, we will take a slightly different route which I believe is much more interesting. We start with transmission line theory. This transmission line theory is, although can be directly derived from Maxwell's equations, which we will do so later on, okay, and therefore has a proper electromagnetic basis, can also be thought of as an empirical or a kind of an ad hoc solution which allows us to utilize the concepts of circuits, the same quantities such as voltages, currents, resistance, capacitance, inductance and conductance, to apply to this analysis of these type of structures called as transmission lines. Strictly speaking, transmission lines are part of electromagnetics because they support what we call as transverse electromagnetic waves or transverse electromagnetic mode of propagation of electromagnetic waves, but that kind of a electromagnetic study we will postpone for some time later on. Okay. The subject of transmission lines is actually very important. It was developed earlier to deal with long lines, the power lines that you might see if you go outside. You will see that those power lines are carrying AC voltages at about 50 hertz or 60 hertz, and these lines are actually really long. They are really transmission lines in the sense that they take these AC waveforms from one end of the country to all the way to the other end of the country, right. So these are low frequency transmission lines, and this subject originally started to understand how these AC voltages would travel along from one point to the other point. This is a very crucial thing. AC voltages are actually traveling along as though they are waves. Okay. So this was the origin of transmission line theory, but today transmission line theory is extensively used to not only analyze those low frequency transmission lines, but also very high frequency effects that would invariably crop up whenever you take a high speed behavior or a high speed signal propagation on various devices. It could be a printed circuit board, or it could be a processor, it could be communication inside the two BJTs inside a chip, IC integrated circuit and so on. Okay. So what are transmission lines? Basically transmission lines are devices that allow you to physically connect two elements, one element presumably being the source, which is what is wanting to send some information out, and a load which is taking that load. Okay. So in that context anything can be considered as a transmission line. However, the electromagnetic community considers transmission lines as those structures which are made out of metallic conductors. Okay. So the common examples of transmission lines include this wire, which is actually the small, which is the stranded wire that I have picked up from this one. And of course these wires cannot be used to carry high frequency signals, they can be used to carry low frequency signals. So this is a primitive transmission line, and if I start increasing the length of the transmission line or length of this wire, then we need to understand the behavior in terms of a transmission line. I also have another type of transmission lines over here. This, as you know, is a printed circuit board, and if you look closely you will be able to see these lines. Okay. If you look very closely you will be able to see these lines which we call as the microstrip lines. These are nothing but metallic lines or metallic strips of very small thickness, and these metallic strips are separated from the ground plane, which I have not shown in this one. This is a 4-layer printed circuit board and there is actually a ground plane in between. So these metallic wires are all reference to that ground plane, and you can see that this is a piece of wire or a copper that we have drawn, and this acts like a wire. This is connecting one IC which you can see here. This, we have not populated the IC on this printed circuit board, but we have left a slot here. You can see that there are a lot of wires coming out which actually are connecting to different or coming out from different pins of this particular IC. So you can see that this line, for example, is connecting the output of an IC integrated circuit with this connector. Okay. If you look at the back side, you can also see some more lines which are slightly thicker, okay, but these again are similar in the characteristic of the other one. So, these type of lines on a printed circuit board are called as microstrip lines. Okay. If you look at here, the standard or a very common form of transmission line happens to be a 2-wire line, right, which will be just 2 long parallel wires. Sometimes these lines are connected by some dielectric, okay. So, there is some dielectric out there, but otherwise these are just 2 long parallel wires that you consider. So, these are called as 2 wires, and this is the prototypical example of a transmission line. So, all the different structures of transmission line can be in somehow related to this 2-wire line. This is the cross sectional view. Cross section shows that these are 2 conductors, okay, which are separated by a certain distance. Let us call that distance as some d apart. Another common example which I have not brought here, but you can see it in your lab, would be a coaxial cable. This coaxial cable is a very interesting transmission line. Here again you see a 2-wire kind of a structure, except that the wire is an inner conductor, that is shown here, and an outer conductor. When you want to connect a voltage source, you normally connect the voltage source from inner to the outer conductor, and this outer conductor is usually grounded. Okay. So, this will also be canonically equal to this 2-wire line situation, because there is a inner conductor which is wire and an outer conductor which is another wire, and this is the cross sectional view. Of course, this cross sectional view is not very nice because I have not drawn it very nicely, but there is a circular cross section, there is an inner conductor and an outer conductor. Okay. This is the microstrip line that we have been talking about. So, this is a piece of metal or a metallic strip. Okay. I should have probably written a metallic strip like this. So, this strip will have a certain thickness T, and it would be separated from the ground plane by an insulator, right. So, in the example of the printed circuit board that I showed, the dielectric or the insulator might be epoxy, or it could be the dielectric called as FR4. Okay. And there is certain distance between this metallic piece, and there has to be a certain thickness, the width, and all this will change the properties of the microstrip line. Another line that is closely related to microstrip line is what we call as the strip line. In a strip line, what happens is that you have a inner metal conductor, and you have a top ground plane and a bottom ground plane. The inner metallic conductor is also called as the signal conductor, because that is what carries the signal. Signal is reference with respect to reference to the ground planes. Okay. So, this is one more structure. There is also a coplanar waveguide, or rather which is another transmission line structure, which will have 2 microstrip lines, and these 2 microstrip lines can actually, one of them will be used as a reference, the other one will be used to carry the signal. Okay. So, these are all different type of transmission lines. As I said, its transmission line, the word transmission line is very specifically used by electromagnetic community to refer to anything that is only metallic. Okay. So, although antennas do fall in that range, so antennas are also made out of metals, but we do not call them as transmission lines because it does not connect physically source and the load. Okay. Similarly, an optical fiber is another transmission line in our opinion, but electromagnetic community does not recognize a fiber as a transmission line, simply because this is made on using a dielectric material itself, and the working principle is slightly different from that of the transmission lines. Okay. Similarly, a waveguide is a special kind of a transmission line because it is made out of a single conductor and therefore cannot be modeled with the 2-wire type of a behavior. So, this is also not a transmission line for us. Waveguides need not be only rectangular, they can also be circular, they can also be spherical, you can find lot of variations in that. So, these are different transmission lines, and what we want to study is to kind of characterize these different transmission lines in terms of a few parameters. Now, this is something that would be interesting for us, because whether I am considering a 2-wire line or a coaxial line or a microstrip line, if I am able to model each of these transmission lines with a few parameters, then I can analyze the transmission line behavior without really bothering which transmission line I am applying it to. Otherwise, I should apply the theory to each of these transmission lines separately, and that kind of an analysis can quickly become problematic to us. Okay. So, our goal would be to understand the 2 wire line, because all the other transmission lines can in some sense be reduced to 2 wire line. So, we will analyze these transmission lines in the form of a 2 wire behavior. In order to do that, let us actually write down the 2 wires. Okay. Of course, physically these wires cannot have 0 thickness, there has to be a small amount of thickness. So, let us say I write these wires with this much of a thickness, but I understand that this thickness is actually very small compared to the spacing between these 2 wires. Okay. So, I am considering 2 wires of very small thickness, okay, and the spacing between them is very large compared to their thickness. Okay. There are a couple of additional things that transmission line theory demands, although that is not shown here. It is not necessary that the thickness of this upper transmission line be the same as the thickness of the lower transmission line. Okay. It is also not necessary that the shape of the upper wire be the same as the second wire, the first wire and the second wire. However, there is an important assumption that we are going to make in the initial stages, that no matter what the cross section that we choose, for example, this could be the cross section of the upper wire and this would be the cross section of the lower wire, no matter where along the length of the wire that I go, I must have the same cross section. So, the cross sections here at one end of the wire or at one point of the wires, along this particular plane must be the same cross section here as well. For simplicity and for reasonably accurate description of reality, we consider the cross sections to be of equal shape and equal size, and we also assume that the cross sections are essentially same at all points on the transmission line. Okay. Such transmission lines are called as uniform transmission lines, and instead of talking about transmission, instead of saying transmission lines, I will now use a shorter this one for this called as T lines. A T line is a transmission line. Okay. So, this is a transmission line, and what exactly is the model for a transmission line? You have to understand something. There is a physical world, right? So, there is a physical world in which things happen. So, you have a actual wire, okay, these are physical wires out there, but then when I capture them using a mathematical model. So, I capture this physical world using a mathematical model. A model is a description, it need not be mathematical, it could be visual or graphical, it could also be computational. Okay. So, a model is our picture of what really is happening in the physical world. A simple example is this. Suppose there is a car which is moving along the highway at about say 100 km per hour, right. When you want to describe this movement of a car and calculate its position or its velocity, you do not normally worry whether the car is a Fiat or a Hyundai or some other car, right. So, you kind of approximate all of that and say, okay, I have a car which is moving with this speed and I want to know how much distance it would cover in a given span of say 3 hours or something, right. I am just giving you some arbitrary numbers, they do not really mean anything. What I want to say is that a car is a physical system, but when we model this car, we model this as a small point particle as though its entire mass is concentrated at a particular point. This is called as the mass point or the point mass approximation. So, my car, truck, scooter including ourselves will all be modeled as a mass point. This kind of just simplifies the behavior, like to the equations that turn out to be, the model that turns out to be simple, and it is also reasonably accurate. If you are not happy with this point mass approximation, you can then go to a slightly different model or a more involved model and so on. So, modeling is an art in which you describe or abstract out the behavior of the physical world in so as to generate a reasonably simple model, okay, characterized by certain parameters which you can then measure and keep track of it. Okay. If you want more detailed model, you of course can go into very detailed physics or detailed models of this physical world, but then the complexity of the model would also increase. So, it is always a trade off between how simple and accurate your model is, that is the best solution, or how complex and accurate your model is. Depending on the situation, you might be able to get away with simple and reasonably accurate, or you might want to do a complex, very accurate models. So, having said what that model is, what we are interested is to get to the model of a transmission line. So, we will imagine that we have an infinite length of transmission line, which of course is not really possible, but we will just say that the length is very large compared to the thickness, compared to the distance. Okay. First of all, we had assumed that the thickness T was very small compared to D, which was the spacing between the models, spacing between the wires, and now we will assume that the length of the wire or the two wire transmission line that we are considering is much larger than the spacing between the two wires. So, in a sense I am considering a very long wire, okay, and therefore I can kind of ignore this spacing, okay, but that is what it is. But now if I look at one section of a transmission line, okay, I might identify two things. First, from my physics knowledge, I know that if there is a current flowing here, right, it will then, in this short piece of wire, it will then induce a certain inductance, because a current carrying wire has a certain amount of self inductance associated with it. In this case, there is also mutual inductance from the other one, but let us not worry about it at this point. And by the way, if there is some current flowing into this point here or this piece of wire here, there has to be a reverse current also flowing of the same magnitude, okay, because current has to be closed. But right now do not ask how this current can be flowing when you have an infinite wire, just take this as on a faith at this point, things will become clearer later on. So, I have a current flowing here generating a piece of inductance here or generating inductive effect, okay, and similarly when I take any two pieces of wires, right, between the two, then there has to be a capacitor in between that, right. These two pieces of wires are simply two metals. I am pushing charges on one end and I am pulling charges from the other end, right. As the current flows away from it, it is pulling the charges. As the current flows into this one from the top wire, it is pushing the charges. So, anywhere where you have two pieces of conductors being charged and by being pulled and put in the charges, it will lead to capacitive effects, right. So, there has to be a small capacitance here and there has to be an inductive effect. Now, this picture would be the same no matter where I go on the transmission line, okay. Let us say I am here at a plane called Z, I take this axis to be the Z axis, I am at some particular plane called Z and I am also at a particular plane called Z plus delta Z, okay. This delta Z is actually very small, this is especially small compared to the shortest wavelength of the source that I am connecting. We will see this rule later on clearly when we talk of high speed signal propagation, but for now just assume that this delta Z plane which I have considered or Z plus delta Z plane that I have considered is actually very close to the other plane, and that distance between the two planes is very small compared to the shortest wavelength of interest. Again there has to be a inductance here, right, because there will be some current flowing into it, but it will not be the same current because the current here flowing would be I of Z, correct, and the current that is flowing here would be I of Z plus delta Z, right. Similarly, there will be a capacitance here, okay, but that capacitance or the voltage across this capacitance will not be the same. So, the voltage across this capacitance at Z will be V of Z, the voltage across this capacitance will be V of Z plus delta Z. This is just to denote that voltages can change along the piece of wire, which is what a transmission line does. Similarly, current at one point or one plane will be different from current at the other plane, but what is interesting is there is an inductance associated and a capacitance associated with these currents, okay. You might also ask, have we considered the wires to be ideal, that is, have we not neglected the resistance that the wires offer? You are right, we have neglected resistance of the wires because that makes our equation simple, and once we understand this regime of operation, it is very easy to include the resistance and conductance of these wires. Why would a conductance be present? Because there is a dielectric here, right, and whenever you charge a voltage here, ideally if the dielectric is ideal, you do not see any leakage current, but in practice you would actually see some small amount of leakage current, okay. This leakage current can be modeled by a conductance. So, I am considering ideal lossless transmission line, okay, uniform ideal lossless transmission line or uniform lossless transmission line, in which I am going to ignore the resistance of the conductors that make up the wire as well as the resistance or the conductance of the dielectric. So, both dielectric is assumed to be ideal as well as the wires are assumed to be ideal. So, this is my transmission line. Okay. What is the idea behind this one now, considering at two different planes? The point is that there is an inductance here and there is a capacitance, and this inductance and capacitance are associated at every point along the transmission line. So, these are actually termed as distributed inductance, okay, and this distributed inductance is measured in the units of Henry per meter. Okay. These are not point inductances, these are not inductances of say 10 Henry or 20 Henry. These are inductances which are distributed at every point along the wire. Every short section of the wire will have an inductance associated with it, and between every two short sections of a wire there will be a capacitance. So, these are not localized, but they are distributed. If inductance and capacitances are localized, then we call them as lumped inductance and lumped capacitance. They are kind of lumped together, but these are not lumped, they are there at every point on the transmission line. So, I have L and C, one is distributed inductance and the other one is distributed capacitance. Okay. Capacitance is measured in farad, but we have distributed capacitance which are measured in farad per meter. So, if I consider a short piece of length of a wire which is delta Z long, then the total inductance associated with this one will be L delta Z. Total capacitance associated between two sections of wires which are delta Z will be C into delta Z. Okay. Now, we proceed to look at the equations that describe this behavior. So, as I said, you have a transmission line, and at each section I have an inductance and a capacitance. So, I consider a particular section where I have some inductance. Okay. The total inductance is L into delta Z, because L is the inductance per unit length, and the total capacitance is C into delta Z. I am putting all my inductances and all my capacitances only from top wire to the bottom wire. Actually, I should also include the inductance of the bottom wire as well as capacitor has to be split between the two. But these equations that you get will be the same equations that you would obtain if you associate all of the inductance to the top wire and all the capacitance to the bottom wire. So, there is no problem if you do this particular way. Okay. So, at every node sort of thing you will have, so this is the plane that I have considered at Z, there will be one more plane here, okay, and this plane will be at Z plus delta Z. So, this is at the plane Z plus delta Z, this is at a plane Z, this clearly is a plane at Z minus delta Z, and this structure does not end, it keeps on going forward in this particular way. Okay. There is a current flowing through this which is I of Z, okay, and the voltage across these elements would be some V of Z. Okay. So, this is V of Z, and there will be a voltage here which is V of Z plus delta Z, and there will be a current which is flowing through this one. Can I just rewrite this one? The model would be slightly better if we interchange the positions of inductance, if we change the positions of the capacitors. Okay. So, the proper model will be something like this. So, I consider these planes at Z and Z plus delta Z. So, this is my plane at Z, this is my plane at Z plus delta Z, and this is a plane at Z plus 2 delta Z, and so on. This of course keeps continuing. The voltage here will be V of Z plus delta Z, and this current will be I of Z, and the current through this one will be I of Z plus delta Z. So, this is the current that is flowing into the inductance that is between Z and Z plus delta Z, and I of Z plus delta Z is the current that is flowing from Z plus delta Z onwards to the next section of the wire. The voltage across this capacitor is V of Z. Okay. Now, I know from circuit theory that I can apply KVL and KCL, right, Kirchhoff's voltage laws and current laws. I consider this particular loop. Okay. Into this loop, if I apply the Kirchhoff's voltage law, I know that this would be minus V of Z as I go from bottom wire to the top wire, this would be minus V of Z, and there is a current flowing through the inductor. If there is a current flowing through the inductor, what would be the voltage across the inductor? That would actually be L into di by dt. But in this case, my current is also dependent on Z, because I am considering that current will change from one Z to the other Z. Therefore, I cannot use di by dt, I have to use del I by del t. So, that would be plus L delta Z del I by del t, remembering that I will be function of both Z and t, plus there will be a voltage at delta Z. This is at the same time t, so I have not shown the time dependence here. I will show that one later on. So, this sum of voltages must be equal to 0. If you rearrange these equations and then divide everything by delta Z, what you get here is this equation, which is a interesting equation, because I can then go to the limiting procedure of making these sections to be as close as possible, or as close as possible that I want, and as I shrink them, that is, as I bring these sections closer and closer together, right, what happens is that the inductance there becomes again as it is distributed, but the sections start to become very small. But there is no problem with this limiting procedure, because I will be adding more and more sections here, right. As I bring these two together, I will have more and more sections within the same earlier distance. So, this limiting procedure is very well done, and for physical reasons the voltages and currents are not running off to infinities. Therefore, the left hand side of this equation, the right hand side I do not need to limit anything, because there is no Z dependence there. So, on the left hand side I have, as the limit delta Z goes to 0, this equation is nothing but the partial derivative of V with respect to Z, and therefore I can replace that one by, that must be equal to minus L del I by del t, I being a function of Z and t. Similarly, and I leave this as an exercise to you, I would like you to obtain an equation by applying KCL, okay, to one of the nodes that we considered in the previous case. So, you can apply KCL to this particular node, okay, which will have some incoming current and an outgoing current. The difference between incoming and the outgoing current will be the voltage across this one. So, if you apply the Kirchhoff's current law at this node, which I have shown here with the red dotted color, you see that there is an incoming current I of Z and there is an outgoing current I of Z plus delta Z, right, and the difference between these two currents must be used to charge the capacitance. So, you will have minus I of Z plus I of Z plus delta Z. My notation is that incoming current is negative and outgoing current is positive, right, and this difference between the two must be because of the current that is being used to charge the capacitance, and that charging current across through the capacitor will be C into delta Z, because remember C is capacitance per meter, delta Z is multiplying that. So, this term must be equal to 0. As before, you can do limiting procedure by dividing on both sides, I mean dividing everything by delta Z and then adjusting the currents at Z plus delta Z and Z, and to end up with an equation that would be like an analogous equation to this fellow, right. So, you will have an equation in which the rate of change of current with respect to Z will be given by minus C del V of ZT by del T. Okay. Now, you can actually consider these two equations and then try to solve them. Okay. Normally what we do is we consider these equations in pairs and then we reduce this first order partial differential equations into second order partial differential. The way to do that one would be to differentiate the voltage equation with respect to Z, okay, and then utilize the other equations, okay, in order to show that you can compress two first order partial derivative equations or partial differential equations into a second order partial differential equation of this particular form. Okay. I have of course derived it only for the voltage. This consists of actually differentiating this one with respect to Z and then differentiating this one again with respect to time and then recognizing that there will be term of del I by del z, del square I by del t del z on both sides, and then substituting one into the other. It is a fairly simple exercise. Please follow it up and then show that the voltage will satisfy this equation. You can also show that the current equation will be the same. It will be del square I by del z square is equal to L into C del square I by del t square. In both equations, you should remember that voltage is changing both as a function of z as well as a function of time. Similarly, the current is changing as a function of z and t. In the next module, we will look at the solution of these two equations. Thank you very much.